Look, I get it. We're probably tired of hearing about all the doom and gloom surrounding climate change, all the consequences of climate change, and all the money that's involved in climate change. Like, I know we as Canadians are sick of hearing about carbon taxes and all the money that we have to pay as out of pocket to help climate change. However, today we're going to switch it up a little bit. We're going to talk about climate solutions. No money from us, no carbon tax, no taxes at all. We're just going to focus on climate solutions. And today on the program, we have Dr. Annalisa Bracco, who's a professor and associate chair for research at Georgia Tech School of Earth and Atmospheric Sciences, specializing in ocean and climate dynamics. Not only is she specializing in ocean climate dynamics, she also has experience working out in space. And she talks about how familiar things are in space as they are into the ocean. We're going to hear all about that and her projects as she's been collaborating with a number of different engineers and scientists and business people on climate solutions on this episode of the How to Protect the Ocean podcast. Let's start the show. Hey everybody, welcome back to another exciting episode of the How to Protect the Ocean podcast. I am your host, Andrew Lewin, and this is the podcast where you find out what's happening with the ocean, how you can speak up for the ocean, and what you can do to live for a better ocean by taking action. Now, today's episode, we're going to be talking about climate solutions. And before we get to that, if you want to know more about what you can do to help protect the ocean, you find out more information from us, you can go to our website at speakupforblue.com. All you have to do is go to speakupforblue.com. And then if you want information to your inbox to find out more about the episodes that we release, to find out more about the news that's being released on the ocean, and you can find out more about jobs that you can search for to follow a career in marine science and ocean conservation, just sign up for our newsletter. Go to speakupforblue.com/newsletter. That's speakupforblue.com/newsletter. Let's get into the episode with Dr. Annalisa Bracco, who is a professor and associate chair for research at Georgia Tech School of Earth and Atmospheric Sciences, specializing in ocean and climate dynamics. And as I mentioned before, she was like a physicist that looked at space and looked at how galaxies were formed and how planets were formed and modeling all the stuff around there and how similar space is and modeling space is compared to the ocean. Very, very interesting. We talk a lot about climate solutions. We talk a lot about how she was told by her own father that you wouldn't do well in physics because you're a woman. And we'll see what happens with that. She became quite interested in looking after things about physics and pursuing all things surrounding physics. And she is here right now to talk about her career, to talk about climate solutions, and why she switched from just modeling climate change to climate solutions. We're going to talk about that today. Enjoy the interview with Dr. Annalisa Bracco, and I'll talk to you after. Hi, Annalisa. Welcome to the How to Protect the Ocean podcast. Are you ready to talk about ocean climate solutions?
Absolutely.
Love it. I love it. I'm really excited about this episode because a lot of the times when we talk about climate change in the ocean, we really focus on the doom and gloom. We don't talk a lot about solutions. And today we're going to be talking about some of those solutions. A lot of it is experimental. A lot of it is in the research phases, but it's really great to be able to look at hope down the way. And I think that's what we need a little bit in today's world. We need a lot of hope. So I'm looking forward to being able to discuss that with you, Annalisa. But before we do, can you just let us know who you are and what you do?
Absolutely. So my name is Annalisa Bracco. I'm a professor at Georgia Tech in climate and oceanography. My background is in physics. So my bachelor degree was in theoretical physics, and I got that in Italy at the University of Turin. And then I did a master thesis or research work looking at the formation of galaxies.
Oh, wow.
And from that, I entered in a PhD to study the role of vortices in the formation of planets. And I do all of that using numerical models.
Okay.
And then after a couple of papers on the planets, and how they form after the star has exploded, has formed. So we have the sun, we have a proton nebula. We need to figure it out how we aggregate stuff to get to the planets.
Right.
After doing that, I was essentially asked by my advisor to get closer to our planet and work possibly in the ocean or in the atmosphere because he was kind of switching research.
Mm,
The equations that describe the motion of the gas around the star or of the oceans are the same.
oh,
You may
interesting. Okay.
make very different approximations, but at the end of the game, the players, the big players, are exactly the same because when you have a star and you have a nebula around, what happens is that the nebula is rotating around the star. So
Right.
you have rotation, and then you also have stratification
Hmm.
because all the gas and the gas, it's all around, and instead the heavy stuff, so all the dust that forms after the star explosion, coalesce in the center.
Okay.
And so you have a thin layer of a dense object that
Right.
is rotating. And that's really what the ocean is a relatively thin layer on a big object,
Right.
which is rotating. And
Okay.
so really the equations and the forces at play are very similar. So it was a relatively simple switch. I love to sail. I love the ocean. And
Hmm.
so from my side, it was very easy to pick the ocean against the atmosphere. I ended up also working on the atmosphere. I have nothing against the atmosphere.
Of course.
But at the time, I said ocean, and that stick with me. And I definitely do more research related to the ocean that I do related to the atmosphere.
Phenomenal. I love that because a lot of the times when you hear people talk about space, like say government talks about space, or you hear like SpaceX or whatever, and we're like, we want to go to space. We want all these billionaires are wanting to go to space and stuff and explore space. A lot of times, like, well, let's forget about space. Let's focus on the ocean. It seems very divisive. You know, it seems very like people are pitting one against the other. But why can't we do both? And I love the fact that you have the similarities in terms of the equation and modeling the ocean and out in space and formation of galaxies. And are they're all actually all similar. So we're here arguing like let's spend less money on space, let's spend more money on the ocean, which I get, but in realities, maybe some of the models that were used in for space can be used for the ocean and vice versa. It's just a matter of finding those similarities. So I love the fact that you've crossed over that. But I have to ask to go back a little bit and talk about your interest in physics as a young woman, right? What got you into learning about physics? That's not something you hear every day. And to be honest, and this is a feat to you, is as a woman, you don't see a lot of physicists come out, right? You don't see a lot of women being known as being physicists. So how did you get the interest, and how were you encouraged throughout your time?
I was not very much encouraged for a while.
Okay.
So that's a very different story. So my dad is a self-taught physicist, essentially. My
Self-taught.
yes, my
Wow.
dad only managed to get through a middle school. This
Wow.
was, he was born
Right.
just before World War II, so there was kind of no money.
Of
He had to go to
course.
work, and he actually managed to get through middle school just because some teacher really
Right.
pushed his father to let him do it, because the
Gotcha.
problem was really the family needed him.
Right.
But then he got into the army. Because that was a safe job and a
Yep.
job that pays you every month,
Right.
when he was very young. And from there, so
Was
this
this
is
pre-war or post? Was this post? This is post-war.
post World War II.
Post World War II. Yeah.
And essentially, he got in what here will be the Corps of Engineering,
Okay. Yeah. The
the
Army of
equivalent of that.
Engineers. Yeah.
Yeah, and so they were building bridges. They were rebuilding the whole infrastructure for Italy,
Right.
and especially train bridges. So
Right.
for the rail system. And he started studying on his own. And then in 1969, there was the opportunity for people that didn't have a high school degree to take an exam and get through, and if they pass, enroll at the university. So he did that.
Oh. Wow. And how old
Um,
was he? How old was he in 1969? He would have been what?
he was
40s,
30,
30s?
35, yeah,
Yeah. Okay.
30,
So fairly
34.
late to think about university, but maybe not at
Yeah,
that time, right?
he was already married. My mom really
Right.
pushed him to do that. He had this passion for physics. He had read and learn a lot on
That's
his own,
amazing.
just reading
That's
books
amazing.
and things. And so he passed, but then decided to stay where he was and not go to a university because that
Mm.
would have delayed having a family and things like that. So
Ah, okay.
I was born a couple of years later, in fact. But at the same time, that allowed him to advance in the career in the army as if he had a high school degree.
Gotcha.
And so he was able to get into the military academy for the Corps of Engineering and teach applied physics. So
Mm.
I grew up with a father that would teach us physics every single opportunity he had. So I do remember, not too fondly, those trips where you know, any kind of something that was moving in the car, and
Right.
we would have to go through the centrifugal acceleration and and always get to calculate, what is the minimum, what is the ideal distance for a satellite
Hmm.
to be in a geostationary position. And I was 6 or 7, and my brother was younger, and so it always came to me to do all those calculations. And of course, I was
Right.
doing them wrongly. I mean, I was
Well,
six
yeah,
or
but you were
seven.
6 or 7. Yeah. Yeah.
So he decided I was really not talent for physics, and but it got me to think a lot about that, and it got me then. Later on, we start talking about general relativity. He had read everything about that too. I mean, the original textbooks by Einstein.
Right.
And so I got to be interested in that. And then one day he told me, but you are a woman and women are
Mm.
not logic, and so you cannot understand physics. And I got
Wow.
so mad that I
Yeah, I
ended
can
up
imagine.
saying, well, I'll show you.
Yeah.
And that's pretty much how I got into physics, really.
So it was more of like to prove your dad wrong, to say, hey, you know what? You've been teaching me all these years. I picked up a few things and I've got an interest in it. I'm going to do it. I like that. I
Yeah.
like that. That's really interesting. And then from there, so that means, high school, if you took physics, and then in university, or how did that work?
No, I took very little physics in high school. I actually went for classic literature. I was very, very talented in
Oh,
literature and writing. So I did Greek and Latin for 5 years and just a
wow.
tiny bit of physics, but I enjoyed that tiny bit. And then I really I mean, I really did physics as an undergraduate because I wanted to show him that I could do it.
I love that.
And in fact, I finished, and before getting into a PhD, I took a year off and I went to do classic literature as a bachelor degree
Hmm.
and decided that I was getting bored because I was missing research.
Gotcha.
My last year as an undergraduate in Italy, it's essentially equivalent of a master. You have to work on a
Okay.
thesis, and I really enjoyed the research part.
Ah.
So I went back and I tried to enter in a PhD, which is hard in Italy, just percentage wise, because it's a exam that you have to pass nationally.
Okay.
So there are
Okay.
very few positions open. Things
Gotcha.
have changed, but
Yeah.
when I
Yeah.
did
But at
it, it
that
was like
point,
that.
yep.
It was like that. And I remember calling my dad and saying that I was dropping a job offer that I had received because I wanted to first try to get into a PhD. And he told me, "You are good, but not that good." And I was like, "Well, I'll show you again."
Do you think he knew what he was doing? Because like the
I
first
don't
time he
think so.
said no, and then you're like, no, I'm going to show him, and then now he's telling you, no, I don't. You're good. You proved his point, but no, you're not that good.
No, when I got in, and I actually placed first in the of the 5 people that were admitted that year. I called him. He's the first person I called, and I said I'm in, and he told me, well, how many got in? I'm like 5, and how did you place first? And how many other women? None. It was completely by chance. At that point, like the following year, there were 3 women out of 5, so it was really
It
by
was just
chance.
who applied, right?
Yeah, yeah,
Yeah.
or the mix at that point. I
Yeah.
mean, the numbers are so small. You start with
Right.
70 people, you have to get down to 5. Some
Yeah.
years will be female, some years will be male.
Right.
But he was very impressed by that. He was really impressed by you put 4
I
guys
love that.
after you.
I love that. Yeah. You're ahead of four guys. You're like, hey, what, remember when you said women aren't logical? What happened here?
Yes.
That's fantastic. So you get into a PhD program and you're still doing, this is not the galaxy work. This was more planets
No, I start,
formation.
yeah, I started looking on, I started working on formation of planets.
Right.
And then I switched to oceanography after about a year. And again,
Yeah, you switched to oceanography to do while you're
yeah,
doing your PhD.
yes,
Okay. Okay.
yes.
Because your
And
supervisor changed.
again, vortices in the ocean
Yeah.
are called eddies are fundamental for oceanography. So it was a very easy switch. The,
But I'm sure, like, and you say very easy. I say no way, because just what you're probably working with on the regular, I wouldn't be able to understand, because you sound much more intelligent than I am in physics. Um, but going from space to ocean, just like from a mind perspective, you're exploring the vastness of space, where you could probably make a number of different discoveries. You could probably do a lot of wonderful things. Now, obviously, you can still do discoveries because there's still a vastness to the ocean, but it seems like there's a little bit more limitation. And I say limitation by a squeeze, right? When in comparison, like, was there a shift being like, why am I going from space to ocean? Did you ever have that thought?
no, I love the space part because I love the just the idea. If it's such a you are learning how everything formed and all of that. But I must say that because I was already working with models, the possibility of applying it to
Yeah.
something where I could have observations or I could at
Mm,
least solve actual problem, it became a little bit less abstract.
yeah.
And we were also at the time where climate change was starting to become a problem.
Hmm.
So no, I was very pleased to do that switch. The fact that I had something to anchor what I was doing and
Yeah.
to see the application of what I was doing directly,
Yeah.
it was important. It was rewarding.
Okay. Can I ask what time frame this was?
So I finished my PhD so I started in 1997, I finished in 2000.
Okay.
So
So
I made the switch around 1998.
right. So I was the reason why I asked was more because of you mentioned climate was we were starting to focus more on climate at that point, and that's true. I remember starting to learn. I went to university. I did my undergrad in '97 to 2001, and that's when I started to really find out more and more about climate. And even though it wasn't necessarily being talked about in the public eye as much up maybe until the earlier 2000s, but it was in the academic sort of circles, it was being
Yeah.
discussed quite a bit. We knew that there was going to be problems 10 to 20 years, and surprise surprise, we have problems 10 to 20 years later, and so forth, even 30 years later. At that point, though, did you see, like, focusing a little bit on climate, knowing where this is going, did you really understand, like, how, one, good for your career this would be because you're working in climate, but also, like, understand the depths of the destruction that climate change could cause in the future?
No, not at the
No.
time.
Okay.
Also because I was a student and
Yeah.
I'm always been kind of optimistic. Like it's
Yeah.
just really curiosity what at the end drives me.
Right.
And the other thing that I would say the ocean was bringing was the possibility to really work at the intersection of physics, but also chemistry and biology, which is something that I had in me already from the university, the undergraduate time. So I wanted to be able to do something that was more interdisciplinary. So I didn't see it coming as much. And
Mm.
also, I would say by we started having satellites and having really good information about
Yes.
climate only in the 80s. So we were just
Yes.
15 years or less than 20 years in. The
Yeah.
trends were not there yet. The record was just too short.
Yeah.
But we were coming out of the biggest El Nino in the century,
Yeah.
the 1996 event, and also what that meant for population all over from India to Africa.
Right.
There was a lot of, we can understand more we need to understand more, and we can also be useful to society. That was interesting, and it was also
Yeah.
what drew me into the field.
Interesting. Okay, cool. Now, after which, you finish up your PhD. What happened? What happened next? Like, where did you go? Did you do a postdoc? Did
Yes,
you?
I did
Okay.
a postdoc. I came to the US for the first time for a long period.
Okay.
I did a postdoc at the Woodsole Oceanographic Institution
Oh,
in
nice.
Massachusetts.
Yeah.
And then I went back to Italy and I worked at UNESCO for 3.5 years.
Oh, wow.
UNESCO has one research center, which is located in Italy. It's called the International Center for Theoretical Physics, and they were growing a group in climate.
Oh, was that in Rome or is that?
No, it's in Trieste.
Oh, interest. Okay. Okay.
And then I came back to the United States, and in December of 2006, I joined the faculty at Georgia Tech.
So you went from UNESCO to the faculty.
Yeah, I had
Living.
another year at Woodsole in between,
Okay.
and then I
Okay.
joined the faculty here. Yeah.
So I know a lot of it was research based, but working for an organization like UNESCO, especially in Italy, where I feel like Italy is a bit of a headquarters for a lot of international organizations. UN, FAO is there as well. UNESCO obviously has an office there. It's a pretty big hub for international type of work and research. What made you decide to pursue one kind of a little get away a little bit of that and not work directly for them, but also move into an academic position?
Well, there were a number of work related, personal related, a lot of things that got together.
Okay.
But I was happy to get to a faculty position because I wanted to work more directly with students. And
Okay.
I truly enjoy advising. So I
Okay.
wanted to have that opportunity and build a group and kind of give also back to the new generations,
Yeah,
the passion, the kind of curiosity that I have, and so that for me was important.
I love it. I
And
think that's very cool.
in Trieste, you can do a little bit of that, and you do a lot
Yeah.
of that with students from developing countries, but
Yeah.
it are usually shorter interactions. Like they
Gotcha.
come for a few months and they
Yeah.
go. So it's a little bit
It's
more
not like a
difficult.
3 to 5 year,
Yeah.
depending on what they're doing, whether a master's or PhD or even a postdoc, where you really get into a mentorship role with that student. And I think that really, yeah, I agree. I think that's a really great feature for academia. And now you've been doing that since at Georgia Tech since then. That's fantastic. Sorry, you were gonna just about to say something. I interrupted. Apologize.
Yeah, no, I was just going. Another thing that really brought me to Georgia Tech that I enjoyed very much was the fact that there was a lot of go and a lot of attention for interdisciplinary projects. So there was a lot of support for that.
Okay.
And so I enjoyed that from the beginning because I started working in collaboration with people in biology, School of Physics, and
Right.
College of Computing, now engineers. That was something that really brought me here
Yeah.
and kept me
Yeah.
here.
Well, and I mean, like, look, Georgia Tech is a great school. It's a big school. It's got a lot to go by. It's very popular. Now, how did you feel about coming from Italy, where you have European football, and you come to Georgia Tech, where you have American football, which is pretty big there? Did you do you
I
go to
don't
the
watch
games?
football. I don't watch American football. I don't
Do you watch
understand it.
European
I don't watch
football?
it.
Do you watch European football still?
I used to.
Okay, gotcha.
I still watch the World Cup.
Yeah.
But
Oh, of course. Yeah. Of course. Yeah. That's awesome. Okay. Just wanted to, I had to push that in there because I feel like that was a big change in there. Now, is there a lot of difference between doing a PhD in Italy and then mentoring PhD students and graduate students in America, like in the US?
yes and no, in the sense that the Italian PhD comes after an undergraduate, and now it's different. But
Now it's different.
anyways,
Yeah.
it's a 3 plus 2 years even now, so it's a 5 years, and essentially you already do the equivalent of a master.
Gotcha.
So when you start your PhD, it's shorter, it's 3 years. and is really focused on research. There are almost no classes.
Gotcha.
While here it's longer and is essentially what in Europe or what in Italy would be the master plus a PhD.
Yeah.
It's 5 years, and the first couple of years there is a substantial amount of coursework that you have
Right.
to take. And so in that sense, it's just putting together the two things. So it's
Interesting.
different, but
Yeah,
at the end,
interesting.
it's
Same amount of time, just
yeah.
different way of focusing it. Yeah. It's interesting because I live in Canada and the research thesis for a PhD is very much research based. You do some
Mhm.
courses if you need it, but there are students who don't. They may do like one or two courses if they need it, but it's very different there. So it's interesting to hear like the European versus North American and the differences and similarities from there. Now, since you've been at Georgia Tech, it's been almost 20 years, I guess,
Mhm.
since you've been there. Has your work has stayed on oceans and climate? How has that evolved over the last 20 years for you, and just sort of how sort of we've been evolving as a society as well?
I think we definitely shift from just understanding the climate system and
Hmm.
trying to attribute the changes in the climate system to greenhouse gas concentrations increasing, to aerosol increasing initially and now decreasing and so on, to really trying to find solutions to the problems and to working much more towards adaptation and mitigation strategies versus just we want to understand.
Yeah.
So that shift is happening.
Yeah, yeah, exactly. And now you are focusing a lot now on, I guess, less theoretical sort
Yes.
of applications and more, I guess, like practical applications, especially when it comes to climate. Why have you decided to do that?
Well, again, I think that if you just identify the problem and you don't work on the solutions, I mean, obviously it's important to identify the problem and understand the problem. You cannot
Of course.
solve it otherwise. But there is a lot to be said for also trying to figure it out what is the best way to address it. And I think Georgia Tech, in that regard, it's a fantastic place to be because you have so many opportunities of collaborating with people that can bring also the solution side,
Hmm.
the engineers, for example. And so it's kind of an automatic thing to do, at
Yeah.
least for me, because
Yeah.
I do like to work collaboratively,
Yeah.
and I really appreciate to be able to have that engagement and do new things all the time.
Of course.
And you learn if you are working with someone that has a completely different background from yours. So
Absolutely. Can you talk about maybe one of the first projects that you worked on where it was more solution focused and where that collaborative effort happened and how that collaborative, like how that networking happened, where you became more on the application side
sure,
and the
I have
solution?
several at this point. There is one that I find extremely interesting, which is about Sargassum
Hmm.
in the tropical
Hmm.
Atlantic. We have had since 2011 blooms of Sargassum in a region of the tropical Atlantic around 10 North where we never used to.
Right.
And those blooms are growing over
Yeah.
time. They're becoming bigger and bigger, essentially. And they are really impacting the Caribbeans and the Gulf of Mexico all the way to Florida because all this amount of the sargassum at some point gets to the beaches and it needs to be cleaned up or it rottens.
Yeah.
It's absorbing a very large amount of carbon dioxide from the
Hmm.
atmosphere to grow, but then is releasing it once it gets to the beaches. And so we have to figure it out why is happening and what to do about it.
Yeah. And
Um,
just to interrupt a little bit, I just wanted to give the audience a perspective on how much actually comes to the coast. I went to Mexico one year, and along the beach, it would go up to my knees in sargassum. Like I was really up to my knees in it, and it was all along the beach to the point where now this was a resort. There were garbage truck or not garbage trucks, sorry, dump trucks of that were just there constantly, just taking being filled up with diggers and being filled up with sargassum, and then they would go and dump it somewhere, and then they would come back and they would do that all day. So that tranquility that you expected on a beach wasn't very tranquil with trucks working, 24 hours a day, just trying to get all that sargassum off. So I just want to kind of put that in perspective to people, like how much is coming along the beach. And that wasn't just Mexico. That was a lot of beaches in the Caribbean, and as you mentioned, in Florida as well.
Yeah, Florida and Caribbeans, I think together are spending the order of 300 millions per year now just for cleanup purposes because you
Wow.
cannot leave it on the beach, otherwise you kill the tourism.
Yeah. Yeah.
So it's a huge nuisance on top
Yeah.
of being bad for the environment if you leave it
Yeah.
there.
Yeah,
Um,
exactly. I mean, even just the smell of a
yeah.
degrading sargassum is gross. Yeah. Yeah. Okay. Sorry, I didn't mean to interrupt. Go
Yeah,
ahead.
so I'm working with colleagues in the School of Biology. I'm working with colleagues in chemical and biogeochemical engineering and in mechanical engineering to try to figure it out why we
Hmm.
have this excess of sargassum now. What is promoting those blooms, and are they going to continue in the future? It doesn't look that we ever had them before. Also from historical records, so written records, we don't have records of blooms this large in that area. But they appeared in 2011. We kind of know why they appeared, why they are growing, not yet, not that clear. So
Right.
I'm working on that. But we're also working on trying to figure it out what to do with all this sargassum. There are several groups, both in the US and in Europe, that are considering essentially pulling it together
Hmm.
when it's possible out at sea and sinking it.
Hmm.
And we need to figure it out how much that costs, also from an energetic perspective, and what could be the damage, if any, that we
Yeah.
do to the ecosystem in the deep ocean if we
Right.
dump those large amount of sargassum. And of course, anything that you do in the ocean, if it's within the 200 miles from the coastlines, also need a policy and a legislation and permits, and so it gets
Yeah.
complicated.
Yeah.
The other solution we are thinking is to collect it and then transform it into biofuels. And that's the colleague in chemistry and chemical and biogeochemical engineering and a
Yeah.
colleague in mechanical engineering that are looking into that. And the problem of converting sargassum into biofuel is that the amount of lipid in the sargassum is quite limited.
Mm.
And so you would need to spend a lot of energy to increase that concentration. So we are looking for ways of doing that in a natural, with some kind of
Yeah.
natural system that can help us in that. And so a colleague of mine, Jeff Davis, is looking into using black fly larvae, which is a fly that lives in the tropics, and it's very good at eating up a lot of sargassum or other material, and is very good at accumulating lipids. And therefore, then you could extract the biofuel from the larvae instead of doing it from the sargassum.
Which is crazy to think about it. If you think about this larvae, there's probably about maybe this big to extract all those lipids and how much you'd have to extract from it.
Well,
It's
also how
insane.
many larvae you must have. But
Exactly. I think a lot of people would cringe at just the fact of seeing that many larvae in one spot.
it's a very efficient way
Yeah.
of doing it, and
Right.
it's not very expensive at all, also from an energetic perspective.
Right. Right.
And those flies have no side effects to humans, so it's
So they're
not
not the
that they
black
are.
flies that bite?
I don't think they bite the black.
Because the black flies up here in Canada, they bite.
Well, but anyway, they will be constrained in a
Exactly. That keep them constrained. Keep them all in one
put
spot.
them all together. There is another that I read recently an article of someone that in the Caribbean is using the leftovers from a brewery that make rum
Mm.
essentially to increase to make a mix of that plus sargassum that
Yeah.
can be converted more
So the
easily.
byproduct of making rum
Hmm.
used to mix with the sargassum to create the biofuel
Hmm.
or to extract those lipids to create the biofuel.
Yeah. And
Gotcha.
another one of just using sargassum that has been shown to be possibly a good idea. This has come from Mexico and is essentially a one-person business or one family or a family business,
Yeah.
and they are making bricks out of sargassum. So they are drying the sargassum and compressing them and making bricks. And one good thing about that is that those bricks seem to be better. So if you make a house out of those bricks, it will resist or it will be resilient towards storms more than
Right.
regular bricks.
So far you've identified two to three things that sargassum, like the byproduct of using sargassum,
Yeah.
would actually help would actually help sort of people adapt to climate change.
Yeah.
So, we have the bricks, which are stronger than regular concrete cinder blocks that are used, I guess, in Caribbean houses and homes that will make them even more resistant to the higher winds that you would see in hurricanes, like the in more intense storms. We also have using a biofuel, which would probably be better than using regular fossil fuels to provide energy for us, which is great. Did I miss one? I feel like I missed one.
No,
Did I
that's
miss?
pretty much,
No,
well,
those are the
you
two.
can sink
Those
it. You can
and you
sink
can
it.
sink it, yeah, because it is absorbing carbon, right? So the idea is to allow it to absorb carbon, but not allow it to release the carbon back into the
Correct.
atmosphere, which would be so. Not only does it absorb carbon, but you can even make it better by creating a biofuel and a more resistant brick that could help in building houses in the Caribbean and the thing. So there's a lot of benefits here, not just one benefit, but there's a lot of solutions for this climate solution. And so are they at in terms, like, obviously the person in Mexico, small business, family owned business, is slowly starting this up. Is that scalable? Do you know?
Yeah, I don't know. Honestly, I've not looked into that,
Right.
the scalability of the problem, so I cannot answer on that one.
That's for economists and
Um,
business people to worry about. You worry about more of the how to get it and how to find out how they grow, right?
we are looking into the scalability of sinking it and the scalability of making biofuel using the black fly larvae.
Gotcha.
So,
Now let's talk about the sinking of it, because I've heard a lot of different things when we hear about sinking, these carbon sources, right? If you sink carbon sources, they go to the bottom. I guess the idea, and you can correct me if I'm wrong, is that it becomes like basically like hydrocarbons again into the eventually going into the seafloor and then kind of burying them in the seafloor, and they don't get released. They just stay there, just kind of like how we see oil and gas pockets that we get now. They're just in the seafloor. The problem with that, though, is like you mentioned before, we just don't know the potential, if there are consequences of sinking that much into the deep sea. We just don't know the ramifications of what could happen. Is that correct?
correct. The deep sea is full of bacteria and viruses and other little animals, and so the impact of having those big chunks of sargassum, it's not obvious. I would say probably is not huge if you can do it far enough from any kind of coastline, because you
Right.
can imagine that when a whale dies and sink, it's not releasing less or
No.
it's not being a
Right.
smaller perturbation than a whole
Right.
patch of sargassum. The problem with the sargassum is that it's going to happen more or less in the same place every year, right? And so,
Yeah.
and it's very, very hard to put forward these kind of solutions without having the data to prove that you're not damaging the system.
Yeah.
And unfortunately, those data are very expensive to collect because you have to sync and you have to send down
Yeah.
cameras and you have to go back,
Yeah.
after 6 months or after a year and try to figure it out what is happening. And so it's just a complicated
Yeah. And
problem.
expensive.
It's
and
yes,
expensive,
absolutely,
right? To do even those
absolutely.
pilot studies where it becomes expensive. It's similar in a way to sort of what people, are worried about with deep sea mining. That's more of an extractive, uh, exercise and an extractive opportunity, whereas this one is more of an addition where we're actually adding more stuff. But like you said, it could happen in the same place. And unfortunately, we just don't. If it's done to scale all at once, we don't know the ramifications of that. If it's done in spots and it's done properly, where it's allocated in different regions, and we can see the breakdown happen, if the breakdown does happen, down in the deep, then maybe it'd be a little bit better. I think the problem is just people just don't know, right? When we
Correct.
talk about carbon capture like that, is we just don't know, and we see that there could be a lot of bad things that could happen, which is probably giving that resistance enough to try it out and start to do some experiments.
Yeah, it's also that, I mean, right now, in order to put those solutions forward, we have to be able to verify what the outcome will be, how
Yeah,
much they will take, how much carbon they will take
yeah,
down, how much they will cost, because there
yeah,
is also a cost associated with going and collecting it. And you have to make sure that the CO2 you use by running your vessel that needs to go out and collect it
true,
is
true.
not
Yeah,
offsetting all
yeah,
the advantage that you get, right?
yeah. It's not going to be sailboats that are going out and putting this
I
together,
mean,
right?
you can
Could
you can
be.
hope to use solar panels and all of that,
Yeah,
but you have to do a calculation and you have to
for
make
sure.
sure that you can do it that way.
Hmm.
And so there are still a lot of questions that unfortunately we don't have answer
Yeah,
to. But I can see the sinking, the conversion into biofuel to be absolutely potential good solutions to
yeah.
the problem. And, they're not going to solve the climate problem.
No, but there could be
But
tools in the
there are
toolbox to
tools
help.
among,
Yep.
yeah, exactly.
Yeah.
The
Now,
toolbox will have to have a lot of tools inside,
yeah,
and those ones could
exactly.
be.
How close for both of those sort of solutions? How close are we to getting some of those answers? Are we, like for the sinking? Have there been any experiments of sinking sargassum?
Yes.
Okay.
And if I'm not mistaken, the a group from Great Britain has done most of that work
Okay.
because they managed to link with a company that would like to do it and get
Mm.
credit
Yeah.
for it.
Yeah. Carbon credits. Yeah.
And so they were sinking Sargassum, I think, this past summer, and they will go back and they put cameras
Gotcha.
and they instrumented the regions where they put it down. And I have not heard from them. I would have to
Yeah.
check,
Yeah,
but
it's still
they're
early.
doing
It's
it.
just summer, so it's still early
Yes.
in terms of even with 1 years of data, you're still going to need multiple years of data to really find out the true difference, if there are any, in the effects on the in the bottom, right?
Yes, but I think that if we can show that clearly there is no major change of any kind and it's
Right.
just, you know, being chewed up by bacteria slowly,
Yeah.
that would be
Yeah, as long
definitely
as you show that there's a
acceptable.
decomposition. Yeah.
Yeah.
Yeah. I think that'd be
And for the black fly larvae, my colleague here is working in a lab and doing some experiments. And my other colleague is advising a PhD student that is looking at how that would scale in terms of cost and in
yeah.
terms of how many larvae we need and
Yeah.
how big needs to be the implementation of the system.
Let me let me ask you this. How many larvae does he have in his experiments? I'm
Oh,
curious.
right now he in the lab. It's pretty small.
Okay, thank God.
So it's
I feel like that's a lab I would not want to go and visit because there's so many. I get grossed out by that stuff. But
no,
yeah,
he's looking at optimizing the mixture of sargassum. If you just give them sargassum, they don't grow all that much. So you have
right,
to add a
right.
little bit of something else that
Yeah,
they really like, especially at
yeah.
the beginning. And then once they pick up and they start growing, then they will eat all the sargassum you give them. So
Gotcha.
they are trying to optimize that.
Yeah,
And really looking at having curves and all the data required to then eventually move forward and put actual data into how we have to scale it.
gotcha. So again, still fairly early stages, but the experiments going on to
Yeah.
give us those results and to continue those results going. That's phenomenal. That's really cool. Are there other projects that you've been working on? Doesn't have to be recent, or it could be a little further, or even recent, that you would like to highlight for this episode.
Yeah, we are working on several projects related to coral reefs.
Okay.
Where we have developed in my group. Again, I'm a modeler, so we
Yeah.
use models all the time, and we have developed a machine learning system, so using a little bit of artificial intelligence to figure it out what is the connectivity among reefs. So essentially, if you have a reef or an area in the oceans where you have a very healthy ecosystem, or anyway, a very important ecosystem that you want to observe and preserve,
Yeah.
possibly. You know that because the oceans, there are currents, it's probably connected to someone else or to something else because
Yeah.
it's probably exchanging genetic material through larvae and
Mm-hmm.
fries, which are the baby fish, with another regions outside this localized area that you're looking at. And because currents are pretty powerful, those regions can be pretty large. So
Mm-hmm.
essentially, I can be in Fiji and I may be getting larvae from a place that is 300 kilometers far away.
Right.
And so I want to figure it out if that's really the case and how far I can go,
Yeah.
depending on the kind of fish or the coral species that I'm considering. And depending on that, I will know more or less how long a larva can survive in the water and
Right.
be, you know, be able to then attach and spawn.
Yeah.
And so we are doing that using artificial intelligence and machine learning, and essentially using satellite data of sea surface temperature anomalies because they are linked to currents and building networks where we can see that. And we have done it in
Right.
the Pacific, we have done it in the Atlantic, and we have done it in the Mediterranean Sea. So that has been really interesting because in the Mediterranean Sea we don't have much in terms of corals, but we have been
Yes.
able to follow the invasions of the species that comes from the Red Sea through the Suez Canal,
Mm.
and in the last 10 years or so have been really damaging the Mediterranean ecosystem
Right.
because we
Yeah, they
have
just take over.
essentially imported tons of lionfish, and lionfish,
Oh.
nobody can eat it, and they destroy everything.
Yeah.
So we have been following essentially how that the lionfish has spread, most likely through eggs brought through the Suez Canal.
That's unreal. Yeah.
In the Pacific, we have been able to look at why certain area in the Coral Triangle is doing pretty well
Mm-hmm.
overall. So
Mm-hmm.
it's sometimes it bleaches because temperatures are going up, and we had very strong El Niños and La Niñas, and usually when those events happen, temperature there really change
Yeah.
drastically.
Yeah.
But nonetheless, they are recovering and
Right.
they continue to be quite biodiverse and relatively healthy. So we have figured that, and usually, so what we found is that the system is incredibly dynamic. And so
Mm-hmm.
in the Pacific, there isn't a single place that, or at least there are areas where no matter what happens, some other area will bring new larvae in within a year time, and usually they don't bleach at the same time.
Right.
You know, one is
Oh,
maybe
okay.
very sensitive to La Niñas,
Yeah.
the other is very sensitive to El Niños. But what happened is that when I have an El Niño, the one that bleaches get larvae from a different place, and whenever I have La Niña, the one that was giving the larvae may receive it
Oh,
from another one. And
because the
so,
currents are different.
yes,
Gotcha.
yes. So year to year, the
Yeah.
variability of the connectivity among reefs
Yeah.
is very different. It's very, very
Yeah.
dynamic. And that has helped the system in certain areas, not
Mm-hmm.
everywhere,
Mm-hmm.
to really stand out as is still doing well despite everything. The same is not true in the Atlantic. And in fact, in the Atlantic, we are not seeing corals recovering as much as certain areas of the
Right.
Pacific.
Now,
And
is
the
that because the
Atlantic,
sources are not changing, or
correct.
is it
There
because,
is that dynamics is not there, the variability
right?
is not there. Essentially, the current system goes from Brazil, Belize, north.
Mm-hmm.
And so if you cut and if you kind of bleach and really damage any point or any big chunk in that trajectory, because the trajectory is pretty much always the same,
Yeah,
you are going to essentially cut the supply of fresh larvae, healthy larvae to Florida and the Gulf of Mexico and the Caribbeans. And so Florida, Gulf of Mexico, and the Caribbeans have been seeing strong decrease in coral
yeah.
coverage, and they are not recovering. They're
It's
not
kind of
coming back.
interesting because we see the output from the Amazon River in Brazil. I don't think we understand how damaging that could be and how powerful that mouth is in terms of that current and then going up into the Caribbean and to the Gulf of Mexico. Is that correct? Like it's a lot of it's pushed by the Amazon?
No, it's really more that temperatures have been warming up,
Okay.
and we are really bleaching systems just because of
Just because the
temperature and
temperature.
other stressor. The Florida and the Gulf of Mexico have, you, it-
Right.
one thing
Local
to be very
stressors.
clear, it's not just that
Mm-hmm.
it's getting warmer. It's
Mm-hmm.
also that we are dumping much more
Mm-hmm.
stuff in the ocean than we used to. And so the Pacific has the advantage of still being more pristine. Just fewer people live on those islands. Some of the islands are completely inhabited, have no people living there. So
Yeah.
there is the stressor in the Atlantic are heat for sure, but
Yeah.
also pollution,
Yeah.
big time,
Yeah.
and overfishing
Mm-hmm.
and having, just weaker ecosystems
Right.
on average.
That's why it's so
Um,
important to have, marine protected areas and
yes,
quotas and
yes,
stressors, or not stressors, sorry, regulations to decrease water pollution,
yes,
all to help these animals adapt to the higher temperatures. So if we take away all the human stressors or most of those human stressors, then
that,
perhaps the corals and other animals have the ability to adapt to the higher sea surface temperatures
yes.
like they have been.
Yes,
Gotcha.
absolutely. So I have a colleague actually just my office on the side who has worked on sea cucumbers.
Oh, okay.
And he has found that, for example, in Morea, where there is a big effort that has been going on for more than 20 years, funded by the National Science Foundation to do a long-term monitoring of the coral reefs there.
Yeah.
Some reefs has been doing much better because sea cucumbers have not been eradicated.
Mm.
Sea cucumbers have become a delicacy in certain Asian
Yes.
countries, and so there
Yeah.
have been fish and really overfish. And sea cucumbers, they discover, and they just published last year, are really the cleaners of the bottom of the ocean.
Yeah.
They
The
remove
scavengers for sure.
yeah, they really remove any kind of virus, bacteria, stuff that you have. And so they help corals to thrive immensely.
Mm.
And so a postdoc here at Georgia Tech, working with my colleague Marquet, was trying to plant corals. You can break a coral and make little corals and plant them essentially
Yep.
in order to reestablish a population that has been damaged. And there were a bunch of sea cucumbers where he tried to do it, and he removed the sea cucumbers. And for the first time, all his corals, little corals, died. And so he made the connection that, usually his efforts have been successful in the past, and so why this time that happened? And he remembered he removed the sea cucumbers, and
Yeah.
so they went
So they're
back and they
important.
started studying it and found that they are essential.
Right.
So that's another stressor that we add just for they're not particularly tasty. There is no reason, it's more of
Nope.
a cultural thing. And
Yep.
gee,
As many
yeah,
times it is. Yeah. Yeah. It's very very similar to like shark fin soup in a way.
yes,
Except sea cucumbers are probably not as iconic as a shark, when we think about it.
exactly.
This is fantastic. This has all been quite interesting. You're working on a number of projects. Is there anything upcoming that you're starting to work on, or you just started to work on that you're looking forward to, and you can share a little bit to for our audience?
Yeah, we are working on a large project across different universities to figure it out how much alkalinity enhancement we could do in the Gulf of Mexico and through the Mississippi River Basin to what is called weathering.
Yep.
This consists in adding essentially pulverized rock
Hmm.
to agricultural fields or directly in the ocean to reduce the CO2 by forming carbonates.
Gotcha.
So the CO2 that is in the air will react with the dust and form carbonates, and then those carbonates will eventually sink if they are in the ocean, or
Yep.
if it's done over agricultural land, will end up in the waterways, and at the end, if it's the Mississippi River Basin in the Mississippi and therefore in the Gulf of Mexico. So we are doing high resolution simulations, so simulations down to 1 kilometer essentially of what it may happen in the Gulf of
Hmm.
Mexico if this is scaled up. And as part of this project, there are also farmers that are trying to see the impact of using fertilizers that
Right.
contain a little bit of the dust. And so really trying to see also at the land level what the impact could be, how fast they will get in the water system, in the waterways, and so on. So this is incredibly interesting because it goes from really land to ocean to the region,
Yeah.
linking everything
Absolutely.
together. So
Showing that watershed effect on the ocean and how important it is to manage not only water and oceans but also land.
yeah.
I think we see it a lot, and you probably see it a lot, especially where you are in Georgia Tech, in terms of the Mississippi plume. We've known for a long time that that plume has a huge effect on the Gulf of Mexico, and everything that comes down, all the fertilizers and all that that come down and cause that big bloom in the spring, and then the bloom goes down into the bottom as the phytoplankton die, and then you get that bacteria that uses up the oxygen to decompose that, and you get basically hypoxic zones
Yeah.
along the Gulf of Mexico. However, if you start to turn that around and start to look at what you can do in terms, like you mentioned, putting in the rock dust onto the fields, getting into the Mississippi or getting into the waterways, getting into the ocean, you can reverse the shift from alkaline to acidic, and really help out not only corals but a lot of mollusks like oysters and mussels and clams and scallops that can help build their shells, and snails and crustaceans like lobsters and shrimp and everything that use calcium, that need calcium in their bodies, right? So I think this is all fantastic. I mean, this must make your work such like a lot better than just identifying the consequences that climate change can cause. How has this changed your outlook, like switching from modeling the effects of climate change to looking at solutions? Personally for you, how has that changed your outlook on sort of what climate change can do and what we can do
Well,
to
it,
change
it
that?
gives me hope that, we are at the point of really thinking about how to solve the problem, or at least how to find solutions that make sense and that can help. Again, it's not a done deal in any
Of course not.
way, and
Yeah.
the portfolio of solutions that we will need is really large because the problem is big.
Yeah.
But I also see, the Gulf of Mexico has also we do a lot of work with NOAA, so the National Atmospheric and Oceanic
Yeah.
Administration, looking at both corals and fisheries and how to best manage them. And there is really a lot of attention in trying to preserve what is left and help with the
Yeah.
resiliency of those systems. It gives me quite a bit of hope.
Yeah. I would imagine.
And I think that, also looking at communities and, fishing communities, fishermen
Yes.
communities, they do understand. So it's much easier today to work with those communities, and they they have seen the changes. They have seen the
Right.
decrease in fish, for example, in the population, so in the ecosystems, the damage, etc. And they want to help. And
Right.
there is a discourse that it's much better than used to be. And and what is great is that the science ivory tower is also coming down a little bit, and we are
Yeah, yeah.
you
That
know
silo has come down, and you're getting more
yes,
into the community. And I think it's a
yeah.
benefit for not only for you as a researcher, but also for your students who get to interact with the community and be able to work on projects very similar to those, or maybe building on the projects that you're already working, or even expanding those projects where we're seeing more and more solutions and increasing that hope. Because look, we know one solution is not going to solve this. It's going to take a lot. It's going to take a lot of people, and to be able to collaborate, which is a huge part of science, as well as conservation, and to be able to find these solutions that, whether it's one or two or three or all of them that work out, then that's a benefit to us, a net benefit to us. And I think
Tomorrow I have a phone call, I have a Zoom call with pro program managers and a student of mine and a colleague of mine in mechanical engineering, because we would like to learn how coral listen, how coral larvae respond to sound,
right.
because we think that that will really help restoring some of those coral reefs. And it's
Yes.
just unbelievable. 15 years ago, we didn't even think how.
No. Yeah. Yeah.
And, we have a problem, and there are a bunch of people trying to solve it. And
Yeah.
so we can also think of using sound or chemical cues and trying to
Yeah.
figure it out it is just amazing.
Well, and what I love, it's combining that research of discovering these amazing things and then putting it towards a solution that can help rebuild these very important habitats, and hopefully find ways, just like you did in the Southeast Pacific, like in near Indonesia, where in the Coral Triangle, where there are some corals who are doing really well. Why are they doing really well? Because then you do the research and you figure that out, and maybe that can be duplicated somewhere else, or
Yeah.
that could be, we can find similar patterns and trends, because that's what science does. And I love what you're doing, Annalisa. I think it's fantastic, and I want to thank you so much for coming on here and sharing your research with us, as well as your collaborators. I think this is something that we need to see and hear more of. So I really do appreciate you coming on the podcast and sharing that. And I would love to extend another invitation on to discuss more of the projects that you've done at a later date, to be able to get updates on the projects that we discussed here and learn more about some of the other projects that you and your colleagues are working on. It'd be really great for us.
Sure. I will be
Awesome.
very happy.
Awesome. Well, thank you very
Thank
much for
you.
joining us. We really appreciate it.
Thank you, Andrew.
Thank you, Annalisa, for joining me on today's episode of the How to Protect the Ocean podcast. It was great to be able to hear about your career, your determination, your motivation to prove people wrong, including your own father, which I think is really great, and to show how well you can do with that motivation. And where you're at in your career is unbelievable. The stuff that you've accomplished and the stuff that you're helping to accomplish by looking for solutions on climate change. I just think it was really cool to talk about how we can use a problem, like a pesky problem like sargassum, just accruing on the beaches and accumulating in the amount that it is on the beaches. As I mentioned, like I went to Mexico and there was knee deep in sargassum, and people don't like it. Sargassum doesn't really feel good on the feet or on your skin. It's a little rough, and people just don't like it. They think it's gross, and nobody wants to swim on a beach like that. So imagine taking that sargassum and doing something good with it to either sink it or make biofuels out of it. I just think it's absolutely amazing. And to look at the different things, like to use actual black fly larvae to be able to accomplish what you need to make biofuels out of sargassum. I think these are types of solutions that we need to find out. We need to do everything we can to get to solutions, and not only just one solution. We need to find many solutions, because it's not just going to be one and done. We're not going to find one solution that's going to fix everything. It's not going to be fixed right away. It's going to take a long time to do so, but we need to do everything we can to do that. So I think Annalisa is on the right track. I think she's really showing by leading as usual, and that motivation to say, hey, you know what? You can't do it. She can do it. and then she will show you and more. So I just thought it was wonderful. I'm going to link to all of Annalisa's links so you can connect with her and you can follow her. And also, if you want to get a hold of me and DM me on how you thought of what you thought about this episode and what you think about Annalisa, I would love to hear your thoughts. Just hit me up on Instagram, DM me at How to Protect the Ocean. That's at How to Protect the Ocean. And of course, if you want to follow for more, you can do so by subscribing, following on YouTube, on Spotify, on Apple, and your favorite podcast apps, and you'll be able to learn more about how you can protect the ocean. So thank you so much for listening to this episode of the How to Protect the Ocean podcast. I am your host, Andrew Lewin. Have a great day. We'll talk to you next time, and happy conservation.